chapters 13 to 17, right, we started the whole class talking about the kinematics of particles, describing motion for collection of mass at a point, right? So it's not really realistic except, you know, for very small objects, but it also greatly describes the center of mass for, you know, mass distributions, right? The center of mass of a true object that has a distributed mass acts like a particle, right? So that's why this is so important. So we started by, you know, describing rectilinear motion, right, with, you know, talking about, well, the specification of the acceleration changes our analysis. We then moved into curvilinear motion and talked about three, you know, introduced ourselves to the coordinate systems, Cartesian, natural, and polar. And then relative motion, which now, right, having some hindsight, how much do we use relative motion later on in the semester? We then moved in kinetics, which is now introducing, you know, an analysis of the forces that cause the kinematic motion that we spent so much time describing. And really at the heart of the entire semester was force equals mass times acceleration, right? I mean, that's the name of the game. That's everything we did is built into right there. Kinematics all there, kinetics there. You know, we dot this with position vectors and we got work. With an integral, we integrate this in time, we got momentum. We extend this to 2 dimensions, 3 dimensions, and we got the whole rest of the class with rigid body kinematics and the 3D rigid body kinematics that followed. Okay, so that's force equals mass times acceleration. We talked about the force mass acceleration relationships. We then, you know, converted this to work energy and talked about kinetic energy, potential energy, basically conservation of energy, where we might have some non-conservative forces that cause a loss in this energy, right? And this is the term that we need to then integrate through the path to determine the magnitude of that. We're going to talk more about this when we get to the newer material review here. And then we talked about momentum ideas, both linear and angular, and how conservation of linear momentum during a collision is a good an analysis technique. Okay, we then wrapped up chapter 17 introducing rigid body kinematics. So now the description of motion for objects, you know, objects that take on a mass distribution, limited to planar motion here, right? So here are our two relationships where we had these terms, relative velocities that allowed us to analyze sliding contacts. But if we are truly on the same body, then those are 0, but we still get these extra terms that due to the fact that the actual body itself is rotating and maybe angularly accelerating, right? Okay, now these, remember, were the velocity and acceleration of particular points on that rigid body that was moving with omega and alpha as its angular velocity and angular acceleration. And we were writing this in terms of, you know, another point on the body B. We then extended our rigid body kinematics to rigid body kinetics, again, analyzing the forces that cause that motion. We started by, well, we still did the 3 same analysis techniques, F, force, mass, acceleration, then work energy, and then momentum that allowed us to analyze impacts or collisions. Force, mass, acceleration, the procedure for there was draw out a free body diagram, work through kinematics as required, right? So our rigid body kinematics that can relate the acceleration of the center of mass, the angular velocity and acceleration of that rigid body. We then wrote out the equations of motion, right? That's why we needed to get the acceleration of the center of mass, g. Right, the first equation of motion here was sum of the forces equals the mass times acceleration of that center of mass. And I want to put here, I just thought this right, this is actually 2 equations for planar motion because we're limiting our motion to be in a plane, and then the rotation is an axis out of that plane. Okay. Then we had different versions of the moment equation. Now that we have to deal with, you know, rigid bodies, our motion is also angular. We had 3 different versions, right? This would be analyzing the rotational kinetics about a fixed point, about the center of mass, and then about an arbitrary point O. Right? It's 3 different versions. Choose one that was appropriate for the system. And then this 4th step is then solve, based because there should have been enough equations there for the unknowns. Right? Then we looked at work energy for these rigid bodies in planar motion, right? We do this to relate heights, velocities, spring lengths. We basically want to do this whenever we can because we don't have vector relationships, and I don't know, it's a lot of good information, but you're limited into what you can analyze with this, right? You can see it doesn't involve the actual forces if you actually want to solve for that. Our procedure here would start with the free body diagram, as you see in any of the kinetics problem throughout the entire semester. Every single problem I ever did that dealt with kinetics, not just kinematics, we started with the free body diagram. And here, right, that's to make sure that we include all of our forces. We're not forgetting one that maybe belongs in this term. Okay, here's our work energy equation, where the kinetic energy has a translational part and a rotational part. The potential energy has a part due to gravity. Now, this is the height to the center of mass, by the way. Has a linear spring component and a torsional spring component. And then the main way we saw this extra term here, this extra work term, was work due to friction, right? So if it's constant friction over a distance, or an applied moment, right? An applied moment, or this is actually could be any applied force, right? An applied force over a distance, and applied moments over angular changes in position, right? Now, these are positive if the force or the moment is aligned with the position change direction. Okay, I don't know if you can see that. I'll just zoom in here for this time, right? And I just ran out of space, right? But this is basically a valid statement. Positive if the force or moment is aligned with the position change. So if that's a change in translational distance or rotational distance, right, that goes with the force or the moment. Now, it's negative, right? We'd have to put a negative in there if the force opposes the change in the direction, or if the moment was acting in the opposite direction of the angular change. Okay, let's back zoom out. Once we have that, we would expand it. We're kind of talking about how to expand it here, cancel things out if we can, work through any kinematics if we need to, and then solve the system of equations. Okay? All right, the kinematics would then be to relate, like, well, if we're looking for omega, can we write Vg in terms of omega? Things like that, right? Okay, then the third analysis techniques for our rigid body planar motion kinetics is impacts, right? Two bodies making impact with one another but staying in planar motion. Start with a free body diagram. Choose a point where the angular momentum is conserved, whether that's for one body or for the whole system. And then we ask a question, is the linear momentum conserved? That's not necessarily guaranteed. Okay? If angular momentum is conserved, we apply conservation of angular momentum, which says angular momentum of object A about some point O plus the angular momentum of object B about some point O is constant before and after the collision. Right? So we usually said, well, state 1, these two terms equal state 2. And then we cancel things out, right? If linear momentum is conserved, we then apply the conservation of linear momentum. That's fairly similar to what we did in our analysis of particles, but we just do it for the center of mass G. Okay, same thing, state 1 equals state 2 because it's assumed constant, or it is constant for when linear momentum is conserved. And then we might need to work through kinematics to relate these velocities and the rotational motions inside the angular velocity, the angular momentum term there, and then solve the system of equations. And that wrapped up our study of rigid body kinetics for planar motion in 2D. And then the last thing that we've been doing recently is full 3D kinetics or 3D motion. Oops, rigid bodies in 3 dimensions. Okay. And here's my review of that, okay? 3D kinematics, we started with just kinematics, right? This is all just chapter 20, by the way. We started with just kinematics, and we talked about how there was, it's important to distinguish between a primary reference frame, that's usually like the base, right? That with it has a secondary, rotating frame, and then within that there's a body that's maybe rotating with respect to that, and then points A and B are on that body. Right, and then these relations fall out, right? So the velocity of B with respect to A is actually, this is just like particles, right? But it's on a rigid body that's rotating, right? So we have that rotation of the rigid body and then this relative position vector. The acceleration of B is, in terms of acceleration of A at some point A, right? Well, we have this acceleration of the body and then this extra term here. Due to the relative motions of the body. Okay, then we have a way to relate the rotation of the body to the rotation of the secondary axis, and this is really what the nature of the three-dimensional motion is in here, right? The fact that we can have rotation about, the body is rotating with respect to the secondary, and the secondary itself is rotating with respect to primary. And then here's the relationship for the acceleration, angular acceleration of the body, right? Okay, this is just describing the motion, right? Those are our principles. We then extended this to 3D kinetics of a rigid body in 3 dimensions, right? So, and all we did was force mass acceleration relation. No work energy, no momentum principles here. Our general equations of motion are summing the forces equals the mass times acceleration of the center of mass. This produces 3, I call them translational equations because they're just dealing with translational acceleration. And then this now deals with our angular motions here, our rotational equations. And I say ugly just because, right, these are those huge equations that looked really cumbersome. But it turns out to be not too bad if we find a principal frame, which is not, is just what we, often affixing the coordinate system, the coordinate system to the body reference frame at a smart point produces, this effect where all of those products of inertia cancel out. And this is a general way we write it, but really we just go to those Euler equations, and that's why I just underlined it here, Euler equations, and just cancel a bunch of things out, right? Okay, and those are just the last examples we just did. All right, so the procedure, right, for all these, write out our geometry, determine the moments of inertia, and if you have to, the product of inertia. Draw out a free body diagram, work through the kinematics, right, 3D kinematics for the rigid bodies, work through these equations of motion that we have up here, right here, and then solve the system. Right, and that's as quick as we can. Now, I hope you got the idea with just going through this outline that it really was start with particles, then go to 2D or rigid bodies that are moving in only a 2D sense, and then talk about objects in a 3D sense, where along the way we did kinematics first, then we extended to kinetics, where the kinetics came in 3 varieties, which is force mass acceleration analysis, work energy, and then momentum. All right, that wraps it up. So, this is a tough class, so you should be really proud of the work you did. Good luck.